Okay, hello everybody, and welcome to the November meeting of the Howard Astronomical League. We have a really cool meeting today, and we've got an excellent speaker and some announcements. Potentially excellent speaker.
I think nobody can see the slides.
Hey, Victor, we can't see the slides. We
You
can't see anything.
All right, that's just great. So now what do I do?
You have
At the
to,
bottom of the Zoom.
yeah, you have to share that screen. Victor's up for re-election again to be president. You may need to give him another year just to figure out how to do his meetings.
Which screen do I want to share?
PowerPoint, the HAL November monthly meeting. No.
You feel like a lizard.
Like you're trying to conduct an orchestra.
It's not Harry Potter. What was the other guy? He never got it right.
Yeah.
Okay, we can see, I can see it
First
now.
Let me know if you see full screen.
Not yet.
Thanks, nobody.
Nope, we see your presenter display.
Okay.
Now we see it.
Yay!
Okay, I'd like to welcome everybody to the November meeting of the Howard Astronomical League. I appreciate the teamwork, and now we've got a meeting going. So we've got a really cool meeting tonight. I'll just get right into the agenda. So we'll go around, and if there's anybody new that would like to introduce themselves, then we'll do some announcements, including, as Phil pointed out, we have upcoming elections in January for the board of directors. Then we have an excellent, I'm gonna say we have an excellent speaker from JHU APL, highly recommended by Bob Savoy. Then we'll do our normal things about what's out in the sky and go over images. So to start, I'd start with introductions. Is anybody new online? Anybody?
Would you like to introduce yourself?
Sure. Can you see me when I'm talking? Yes, I'm showing it. So I'm Victor Sanchez. I'm the president of the Howard Astronomical League for 2 more months until I run again and am replaced or reelected. And we have some other board members here, but I don't want to embarrass them right now unless anybody wants to. Is there anybody new online or in the room that would like to introduce themselves?
I introduce myself. Name is Travis Totten. I live in Upper Marlboro, Maryland. So fairly new to astrophotography. Just started in June, and shortly after joined this club. So happy to be here. I submitted a couple of images that I'll be happy to share.
Travis, I am having a hard time believing that you just got started in astrophotography in June of this year.
Yeah, I've just got my at a mount in my telescope in June. Yep.
Wow, that is impressive. I've foreshadowing, but Travis submitted a couple of really amazing shots that I'll be showing later. Welcome to the club, and I hope well, usually when there's new members, I say you can come to members events and we can teach you stuff, but maybe you can come and teach us some stuff.
Yeah, I've been meaning to come out. It's Saturdays kids just have so many activities. It's kind of hard to get out there in time.
Yeah, well, maybe we'll see you at an impromptu or something like that. Or
Absolutely.
bring the kids to the public events. There's all sorts of scopes to look through.
Oh, yeah. Yeah.
All right, well, welcome.
Thank
Anybody
you.
else? All right, well, without further ado, we'll get right into the meeting. Jim, do you want to chime in?
Yes. So once again, I get to remind you that we have the elections coming up, 24 elections in the next cycle.
Doing the
Victor
wrong
has
thing.
asked me to serve as the election committee chair, which I have accepted that task, and I'll be running with it. The elections will be held at the January 18th meeting of HAL, the annual meeting, to elect the 2024 board of directors. 6 elected positions are president, first and second vice president, secretary, treasurer, and event coordinator. Even though some presently serving officers may run, all offices are considered to be open to all interested HAL members. So send nominations of yourself or others to election@howardastro.org by 7 p.m. on January 17th. And after the election, the new board's term will begin on February 1st, 2024. Any questions for me?
Do you want to be president again?
You were on mute, Victor.
Okay, well, I'll take that as a no. But I do want to say thank you for stepping up and for helping with the elections. It's appreciated.
You're welcome.
So, unless, just to let everybody know, I plan on running again for another year, unless there's somebody who's really, really excited and wants to take over. I would like to stay on, and we'll let other people chime in when the time is right. Thanks for that. Next bit is star parties, and so there's I usually talk about the next star party. There's no more star parties for 2023. And we have yet to sit down with David Stein and the other people who are good about thinking about, you know, what phase the moon is and when the holidays are, and doing a little juggling of dates to coordinate for next year. So we'll do that soon. So stay tuned for announcement. It'll go on the website. Our illustrious webmaster is here, and he will take care of things as soon as it's available. I'm sure he'll update the website as he always does, very promptly. So other than that, though, despite the weather, we've had a few, although today is amazing and kind of nice out tonight. I'm glad you guys are here with us and not out looking through the eyepiece. So keep your eye open for impromptus. And if you're on the meeting and you don't get impromptu notices, then you can go on the website and sign up for those kind of emails. We've had quite a few in the last week or two, just because the weather's been very nice. Yay. And speaking of star parties, the last star party of the year was just this past weekend, the 11th. It was a bit chilly, but we had a good turnout. I think Cheryl Kerr estimated something like, she was counting really carefully. I lost count. She thinks it was 175 to 200 people, guests showed up. And as you can see, I was the picture. I'm afraid to move this mouse. It's gonna here, let me go over here. This picture down here on the bottom right. Yeah, there we go, laser beam. This picture here, this is my telescope, and I had a line like this. I had 6 to 8 people for at least 3 hours. That's nonstop. There was people coming in and out. And here we see Bob Savoy with his excellent activities table with the solar system stuff, and David Stein over here, and nice family pictures. I took a bunch of pictures and then sent them to texted them to the people that were looking through my scope, and that seemed to go over really well. They were really happy that I was able to capture something. Anyways, it was a really good event, a good turnout. The Halo Observatory scope worked great. Ken, Everhart, and Dale were in there, and Cheryl was walking around being very sociable, talking to people, and we had a good experience overall. So hope to see you at the other ones. Again, the idea is to bust out your telescope and share views with people. And then I'll turn it over to our illustrious librarian.
So hello, this month's book of the month. So I'm Crystal Rowland, the librarian. This is actually from my school's collection, but it's also something that could I see it listed online for under $12. So if you're looking for a great book to just have someone who's younger, possibly just interested in not just space and astronomy, but also a little bit of the history of how space technology has expanded over the course of humanity, this is a great book. So the book is called Space Exploration, A History in 100 Objects by Sten Odenwald. And it's a light read. It has essentially 100 objects with a page and a picture showing like what are the fundamental tools and devices and things that have contributed to humanity's search in the cosmos. So it goes all the way back to ancient times when talking about like ancient stone tablets or star charts by ancient civilizations, all the way up to, you know, the Curiosity rover and the O-ring that and going on to the telescopes of today. And so it's a great read, a great table, a great book for the table to just get people interested, a little conversation piece, and a wonderful thing. I'd consider it beginner friendly, has lots of great images and short descriptions, so you can kind of bounce around. I've read about 25 or so of the 100 objects, and the author does a fantastic job at giving you really detailed and interesting history, but tying it into the relevance of how space exploration has changed over time. A little bit about the author is that he, in the early days of the World Wide Web, had started a website where he started the Ask an Astronomer, right? So when you see those web forums of like 3,000 some questions that have been answered over the course of the years that that website was up, this is the same person who started that trend. So highly recommend, great book.
Great, thanks. That's definitely on my to-do list. Okay, so without any further ado, I would like to introduce our featured speaker, Dr. Debra Buczkowski. She's a structural geologist and planetary geologic mapper who's completed projects on rocky bodies of the solar system, including Mercury, Venus, the Moon, Mars, Eros, Vesta, etc. And I'm super happy that she's going to talk about something that we hardly ever hear about, which is Venus. I would like to, there's one, I put in your slides, your like introduction to myself slides.
Sure.
You can skip through them real quick or brief them if you want.
See, up and down.
Yeah, that's it.
Hi. Let's see. Oh, wrong way. So I put together these slides. I gave a talk at Mount Holyoke College in Massachusetts last week, and they asked for about me slides because they're always looking for people to explain how they got into science and what the pathway towards their science was. So that's where these slides came from. This is just a little bit of, please tell me that's a pointer. Yes. A little bit of background, or just, you know, just examples of some of the work I've done. So I do geologic mapping. This is a geologic map of the chlorous basin on Mercury. This is one of the V18 quadrangle on Venus. Most planets have been broken up into 62 different quadrangles, and geologic maps of each of those quadrangles have been made. Venus is woefully undermapped. So do this one. I have studied tectonic features on small bodies like Vesta and Ceres, and even these 3 asteroids are to scale, just to give you an idea of just how tiny Eros is. And then I've done a ton of work on Mars, which is actually what I spoke about last week at Mount Holyoke. But I'm going to give you a talk on Venus because I love Venus, and I'm on a Veritas mission. So everything we can do to push forward Venus science so that maybe our mission will get undelayed would be lovely. This is just I do a lot of field work. I was in Iceland this summer. If you go to do field work in Iceland, you have to get a vehicle that can drive through rivers because they don't have roads out there. I actually got a broken tailbone driving to our field site. But It's always fun to like go through the rivers. Hot springs, I've done work in Hawaii. This is Lava Beds National Monument in California, where we were doing fracture mapping in lava tubes. Meteor crater, has anyone been? Yeah, it's awesome. It's really weird to think though, you go there and it's this big, huge hole in the ground, and that is only 1 kilometer in diameter. If you were looking at a planet's surface, a 1 kilometer diameter crater is the teeny tiny stuff that you ignore. And then you'll see this one on Earth and it's huge and beautiful, and you're like, oh, it's so big. It's not that big.
Okay.
Oh, wrong way again. How is that? Nope.
Here,
Oh, we need to switch to my slides.
oh, yeah, I put both your slides together. I was waiting for the next slides.
We're gonna have to stop. Yeah, there we go. All right. So I am not an astronomer. I'm just gonna put that out there. I'm a geologist. My undergraduate degree is actually in astronomy. So I do have a BA in astronomy, but I went to graduate school for geology, and because I had an undergraduate degree in astronomy, I had a ton of math and physics. So I applied myself towards structural geology, which is the type of geology that would take advantage of all that math and physics I had.
I'm sorry to interrupt. We already have a question.
Oh. Yeah, go ahead.
You just muted yourself, Wayne.
We aren't seeing any slides, or I'm not anyway. Is
Oh.
it me?
Yeah, no, he's gotta show you.
Thank you, Wayne.
You don't like sharing, but
No.
The problem is you shared your slides, so now you have to unshare and then reshare my slides.
Right.
So you can share your screen or you can share your presentation.
So I think we need to do that.
The next Astro School will be Victor Sanchez learning.
Computers are there to make our lives easier.
Yes. We'll push Bob Savoy to the edge. Actually, I'll.
So I don't know if this will make you feel better at all, but every single time we have any kind of meeting at APL, we waste at least 10 minutes, room full of PhDs trying to figure out how to use the AV system. So
and how many PhDs does it take to figure it out?
far too many.
Yeah.
I don't touch it because I'm useless when it comes to computers. I know that sounds funny, but wow, there's even more people online.
So I think we have to share from here, if you don't mind.
Please.
Yeah.
You don't want me to do it.
I like to comment. You're not alone, we do the same thing in that.
This is why they don't do PowerPoint for emergency surgery.
So what I've got here is a little bit about tectonics and structural geology of Venus. Oop, it's
It's
not,
coming.
no, we can't see it.
Try
So
not to move the, we're fighting each other.
I'm not touching it.
I know.
Yeah, but
it's
you're
just-
moving it.
Just hold it still for 1 second, please. That's good, perfect. Now, do you guys see it?
We
I
see the
do.
presenter mode.
Let's present it on.
Wayne, what would we do without you?
Yeah.
Bars in the way, right?
Timer's going.
Yeah.
Well, going on the assumption that not that many people here know that much about geology, I've included a small primer on structural geology so people know what I'm talking about. It's not just a whole bunch of terms you've never heard before and have no idea about. I've also thrown in a little bit about radar observations. Venus, we do not take
I would love to.
pictures of Venus, we take radar images of Venus. Do people online see it now?
Yeah, yes, it looks better now.
Okay, I am picking it back up.
Thank you, thank you very much.
Forward.
We're out of time, but thanks for coming.
I can't get it to work.
I'll flip for you.
Okay. I'm gonna put this down until I need the pointer. And the people online, could they see the, you probably can't see the pointer, can you?
No.
No.
Well, I think I can. I can see the cursor.
You saw a green dot?
No.
No.
Not a
No.
green dot.
Oh, she's-
No,
she's
okay.
got pictures.
We see the mouse pointer.
I
Okay,
can try
that's
to
not
move
me.
the mouse to keep up with your green dot.
Okay, so just as an introduction, I mean, I'm speaking to an astronomy club. I'm sure you already know this, but Earth is not the only body in our solar system. There are 4 gas giant planets, which actually I should reword because there's 2 gas giants and 2 ice giants. There's the 4 rocky planets. Those are the ones I study. There are 3 dwarf planets and counting. And then there's thousands and thousands and thousands of small solar system bodies. And these include the asteroids and the comets and the Kuiper Belt objects and the Trojans and the Greeks. And there's just so many of them, and they're all really, really cool. Next slide. But I studied the terrestrial planets because I am a structural geologist, which pretty much means I need a rocky body. I studied how rocks break. If there's no rocks, there's not going to break. So Jupiter does not do it for me. I have done projects on all 4 of these planets. But today we're going to talk about Venus. Is it going to work for you? It's going to work for him. Let me try.
These 2.
I was doing that. Okay. Venus is Earth's twin. It's similar in size. It's a terrestrial rocky planet. It's similar in mass. It has a very similar interior structure. But is it really its twin, or is it its evil twin? Because the average surface temperature is 460 degrees Celsius. That's 900 degrees Fahrenheit. The atmospheric pressure is so intense on the surface that the only landers that have made it on the surface, the longest one lasted 6 hours before it squished itself like a tin can at the bottom of the ocean. It is a very thick atmosphere, 92 times as thick as Earth's. There's clouds of sulfuric acid, just if it wasn't bad enough already. Things that make it different from Earth also, no plate tectonics. So you don't have to be a structural geologist to have heard of plate tectonics. Venus doesn't have that. And there's no obvious erosion. So basically everything that's ever happened to the surface of Venus is still there, which basically makes it incredibly difficult for us to pick out what happened first and the order that things happen. So, basics. Just going to start with an outline. I'm going to do the basics. I'm going to do a structural geology primer. I'm going to do a little bit of a discussion on radar interpretation. And then I'm going to talk about some of the features that we'll see on Venus, including extensional structures, structures that form because rocks got pulled apart, structures that formed because rocks got smushed together. There's these weird little volcano tectonic structures. This thing is annoying. And then there's this lovely feature called tesserae, very unique to Venus. And then some of the models that have been proposed for why things form the way they do.
If you want, I'll flip for you. Then you don't have to move it around.
I'll just try not
Okay.
I talk with my hands. I'll just put it down so that it doesn't move all over the place. So what is structural geology? Structural geology is basically a 3-dimensional evaluation of how the surface of a rocky body deforms. And sometimes it's planar, sometimes you get folding. But what we want to do is look at the 3-dimensional relationships of stratigraphic units, where stratigraphy is the layering in the rocks. It gives you an idea of how old things are and what formed first and what formed next. It's a very geometric science. It's really good for people who are visually oriented and can think in 3 dimensions. I had a friend who basically taught a class. She got a 5-year grant from NASA to teach structural geology to deaf students, with the thought being that theirs is a 3-dimensional language, and so that their brains were automatically hardwired towards understanding this kind of science. It was really quite fascinating. When you do things like with structural geology, you get a lot of inferences towards the geologic history of the planet. So we're basically able to reconstruct what has happened to the planet over time by evaluating these structures. So when we talk about structural geology, we're looking at specific types of structures, and these include faults and folds. So the kind of fault, we have extensional features like graben, which basically, I'm gonna use this pointer. No, that's not gonna work. So with the graben, you have those straight edges and a flat floor, and those straight edges are fault bounded, which means there's motion along them. You can also just have plain fissures or fractures, which are just cracks in the rock without movement. So when you have a fault, it means that there's something sliding along that fault. There's also contractional features. Some of these are called wrinkle ridges. Wrinkle ridges are a very common feature in the solar system. We see them on Mercury, we see them on the moon, we see them on Mars, we see them on Venus. Then there's also thrust faults. So you have motion along a fault, right? If the motion is going down like this, it means that the rocks are being pulled apart, and that's extension. But if you have compression,
So here's here the camera. There you towards me. There you go.
oh wow, it really moved, wasn't it?
Yeah, I can move it back.
Sorry, everybody. All right. I want everybody to be able to see me. Okay. So if you have downward motion like this along the fault, it means that the rocks are being pulled apart. And that's extension. But when you have compression and you have this faulted surface, the overlying rock is going to be pushed up, and you get something called a thrust fault. And that will result in folds or sometimes these wrinkle ridges. Now on Earth, we study these extensively because they tend to be zones where hydrothermal fluids get trapped. So the oil and gas industry loves structural geologists because we're the ones who find where all the gas and oil is hiding, because it tends to go along these fault planes. But like I mentioned earlier, it's really important towards understanding the history of a body, what's happening, mountain building, what's forming the rocks, what's destroying the rocks, and what's just going on to help keep our planet active. Everyone tends to hear the word tectonics and think of plate tectonics. That's the famous one. It's only one kind of tectonics. Tectonics itself is just the motion and destruction of rock. Plate tectonics is tectonics on a large planetary scale. So we need to be able to interpret radar images. Venus has a very hot and thick atmosphere. Basically, it means the cameras can't see through it. We cannot take a picture of the surface, kind of like the way we can't take a picture of the floor of the ocean. What we need to do is use radar. So we have taken radar images of the entire planet using the Magellan spacecraft. It was sent to Venus in 1978. And we got very high resolution radar mapping of practically the entire surface. And then we haven't been back since. There have been atmospheric missions, things that have taken pictures of the atmosphere, but nothing has gotten under there to see the surface. So what's important to keep in mind with radar is that when we look at a radar image, we are not seeing what we might think we're seeing because our brains are interpreting this as if it's a visual image. When you see this flow feature here, you might think that that means that that is a light colored material. It does not mean that. This is radar. When you see something bright like that flow right there, that means it's rough. When you see something dark like the background material, that means it's really smooth. However, there's a caveat. Sometimes you get a high radar return that gives you a bright image because the composition of the material yields a brightness. And we can't distinguish between the two. So we don't know if that unit's bright because it's rough or because it's a material that happens to be radar bright. This is one of the things we're hoping future missions to Venus will help us figure out. But we do the best we can.
Can you use different wavelengths to help sort that out?
Yes, so there's X band and L band and S band. The field work I did in Iceland this summer was actually queuing that in, and we looked, little segue. We did a field campaign as part of the Veritas mission, which is one of the next upcoming missions to Venus. And the German Space Agency flew radar over Iceland at the same time that we were on the ground, taking compositional samples and roughness measurements. And they looked at it in S, X, and L. And basically, we are going to compare their images to the actual field work, the samples that we were able to take on the ground as ground truthing for those brightness samples, so that when we get to Veritas, we will have a little bit more of an idea of why things were bright in those different bands of radar. Okay. So there's more, just to be extra confusing. If we have a topographically low feature, like a graben, it is going to have a different radar signature than if it's a topographically high feature, like a ridge. So if you see a linear feature and it's got this dark bright pattern, like on the left, or a light dark pattern, like on the right, it can give you hints as to whether or not what we're seeing is a depression or a peak. And so we can use that to help us figure out the topography and the kind of structural feature we're seeing, which is important because while we have really good radar imagery of the surface of Venus, we have really, really bad topographic data. If you've looked at the kind of topography we have at Mars with the MOLA instrument, it's excellent. We've got this really great topography, and we can do all kinds of studies on lava flows and the tectonics and the height of volcanoes. It's wonderful. Mars's topography is 100 meters per pixel. Venus's is 1 kilometer per pixel, where it's good. It can be up to 10 kilometers per pixel, where it's not good. So using tricks like this is kind of helps us try and interpret what we're seeing. So this is just an example of one of these linear features, where if you looked at that, you would be able to pick out whether or not it's a graben, in this case, a graben, or in this case, a ridge. They look very similar until you kind of look at that pattern of bright to dark. Okay, so let's look at some pretty pictures, because Venus is pretty. There's an assortment of different kinds of features associated with tectonic activity on Venus. It's a very tectonically active body, or at least was in the past. It doesn't seem to have plate tectonics. And the gravitational studies suggest that there's no asthenosphere. So,
can you explain what that is?
yes. People, I'm sorry if I'm speaking down to anyone, I don't mean to. I think most people have heard of the crust, the mantle, and the core. There's an alternate way of looking at the interior of a planet, which is the crust, the lithosphere, the mantle, and the core. The lithosphere is it includes the crust and the upper part of the mantle. And it's this upper part of the mantle that's called the asthenosphere. It's the part of the mantle that is soft and gooey. So this is where convection would happen. And it's convection on Earth, for example, that helps drive things like plate tectonics. But when we look at Venus, it's so very dry. There's signs that there's no water in the interior of Venus at all, or very, very little. And so there have been studies that suggest that this is why there's no plate tectonics. It's so dry that that kind of convection pattern in this soft, squishy part of the mantle just never happened, and the soft, squishy layer isn't there. So this suggests that deformation on Venus must be directly related to that deeper mantle, this more solid rock. And that we have some kind of convection happening in there to help drive these features. We do see deformation at a number of scales. The smallest occur as these networks of parallel linear features, like the images I just showed you. And then Venus has a large number of features that are very unique to the planet. So here on Earth, we have continental crust and oceanic crust. There are no oceans on Venus, but what we do have are highlands. And sometimes people refer to this as the continents. These are super high. They're more than 2 kilometers high, higher than the global average of the altitude on the body. So this includes things like Ishtar Terra, Aphrodite Terra, there's Lada Terra. The naming convention on Venus is after females, so mostly goddesses and gods, but then also just women or important women of history. There are some exceptions to this. There's Alpha Regio, Beta Regio, and Maxwell Montes, because they figured they couldn't talk about Venus and not talk about Maxwell. So other highland areas that are smaller, Ishtar Terra is that huge area at the top. Beta, Phoebe, Themis, these are all like little tiny pockets of high material. Everything that's high is very, very, very deformed, extremely deformed. I'll show you some pictures later. Along with the highlands, there are lowlands. This is about 15 to 25% of the surface. It's broad, it's flat, it's about like right there at that 0 kilometer, that equipotential point, the average height of the surface. And these are called planicie. These are the long flat plains. There's Atlanta, there's Guinevere, Lavinia. And then there's the regional plains. This is 65 to 75% of the surface of Venus. It is very, very young. We normally use impact craters to date the surface of features. There's very few impact craters on Venus. This would indicate that the surface is much, much younger than all of the other planetary bodies. We think that this is because there was a huge, massive volcanic event at some point in time in the past that covered everything except for these highland terrains that are still handing up. So it's this very young surface, very young geologically. So that's like about 1 billion years. But that is a number that changes. Some people think it's only 300 million years. Other people have dated it to as much as 800 million years, or all the way up to 1.2 billion. All of these numbers are still significantly younger than Mercury or Mars or the moon. Earth, of course, has a much younger surface, but on Earth, we have plate tectonics, we have erosion, it's very active. Things are always happening on Earth. Things are not always happening on Venus. So we had to come up with an explanation for why its surface was so young. The lowlands and the regional plains are deformed by some of these smaller scale features. There's pervasive wrinkle ridges. We have fabrics of linear structures. And by fabric, I mean, there will be one set doing this, and then there'll be another set doing this, and they'll have these gridded patterns all over the surface. What we're seeing is an evolution in the tectonic history. The stresses that are affecting the planet are changing with time. This happens on Earth, but what happens on Earth is you have one set of stresses, and then erosion works at it, and the signs of that disappear, and then another set of stresses come and make a whole different set of structures. So you can, on Earth, pick apart what happened first and what happened second, because you see this, like, you see something low, and then something happens on top of it, and something happens on top of it, and you can really easily figure out the history of what's happening. Venus, they're all still there. No erosion. Everything that ever happened to the surface is still there. And it's really, really hard to figure out what came first.
So does that mean that the atmosphere is not eroding anything?
So at the surface, the atmosphere is really slow. It's very sluggish and thick. And so practically no wind, as opposed to, say, Mars, where there's these massive dust storms that can block the entire surface. You don't have anything like that on Venus. There's high winds, high up in the atmosphere, but they don't scour the surface. So, extension. These are the graben. You can also see fractures and fault-bounded troughs. These are usually found in sets of small-scale structures, but you do occasionally see extremely large belts of features, big wide belts, comparable to the kind of rift valleys we would have here on Earth, say at the mid-ocean ridge along plate boundaries. So even though there's no plate tectonics on Venus, we are still seeing some very large scale structures. We also see a lot of radial structures, features that are forming kind of in a broad ray around some central feature. So just a reminder from the earlier stream, we've got graben, we have fissures, and we have fractures. So here's a radial set of fractures. Studies have identified over 163 different sets of these radial structures where there's something in the center and then faults and fractures are just radiating away from them for hundreds of kilometers. These are extremely long. They can be oriented around volcanoes. We also see a number of them around a feature called coronae, which I will talk about later. And over half of them are associated with tall domes. So large areas of lithosphere have been forced upward from below, and this is like cracked the surface. So we can see a number of closely spaced extensional lineaments in similar orientation along the surface. This usually happens where the floors lie 1 to 2 kilometers below the surrounding terrain. So these are called rift valleys. One of the best described ones is in an area called Beta Regio. But they tend to be atop these like broad, high areas. Oopsie. Fracture belts can also be characterized by closely spaced extensional lineaments in similar orientation. And I hope you can see this since I can do the pointer for the people here in the room. But so we've got these features and they're all going in the same order, but there's hundreds of them here. These rise hundreds of meters by themselves, but up to 1 kilometer above the surface. Here's another example. So those are all features that would form where the rocks are extending. They're like being pulled apart. But sometimes we have areas where the rocks are under compression. So they're contracting and you get features that form in this compressional regime. So this is where we would get folded rock, like here on the upper left or lower left. And then sometimes we get these features here. This is on the right is a topographic profile of one of the wrinkle ridges. So notice with the folds, it's kind of even on either side of the center. Whereas with these wrinkle ridges, it's really steep on one side and then kind of drifts away. Yeah.
Is it understood what causes these contraction and expansive forces on the rocks?
So a lot of times with the extension, we think it's formed due to the upwelling of magma that would result in a volcano. With the compression, it's a little more difficult. When you have compression, it could be the cooling of this massive lava field. As it cools, it contracts and has a compressive stress. It might also be the collapse of a volcano. So as the volcano rises, the rocks are being pushed apart, but then as it collapses, you suddenly have compression of all the rocks as the volcano basically collapses under its own weight. So wrinkle ridges cover about 80% of the surface of Venus. If you can see these features, they're very wiggly. There's a reason they're called wrinkle ridges. They kind of look like materials that have just wrinkled. They can be hundreds of kilometers long. On average, they're about 10 kilometers wide, but on height, they're only about 100 meters high. So, and I showed you that profile where they're really steep on one side and then kind of peter away long on the to the edge. What's interesting about these is most of the ones on Venus are traveling from the east to the west. There's almost no north-south ones, but there's this regional scale east to west pattern of these ridges, which kind of suggests that at some point in time, we were getting this north-south compression. Why? We're trying to figure that out. That's part of our job. We also find wrinkle ridges in circles around volcanoes. So you'll find those graben, the extension is happening radial, and then circumferential are compressive features. And that is actually predicted by models. It is involved with the growth of the volcano itself. Okay, ridge belts are basically kind of the alternate to those rift valleys we were seeing. So sometimes you have so much extension that you get these big rift valleys that are comparable to the mid-ocean ridge, mid-Atlantic ridge here on Earth. And then other times you get these huge parallel ridges running together, parallel to each other, and just going for hundreds of kilometers, and they're huge. And it suggests a really massive amount of compression. But once again, we're still trying to figure out exactly why these would be forming. So we have lots of ridges, and then compared to wrinkle ridges. Just trying to give you some pictures. So this says volcano-tectonic structures. And if you listened, you'd probably noticed that all of them seem to be volcano-tectonic. They're not just disruption, they're actually associated a lot of the time with the growth of volcanoes. But these are features where you take that and really, really see the volcanic activity. So these are coroni. Coroni means crown in Latin. These are called coroni because they tend to be these very circular features that kind of look like crowns. They're extremely abundant on the Venus surface. There's over 500 of them. They are only found on Venus. We have not seen these on any other planetary body except for a couple of features somewhat similar to them on Miranda, which is a moon of Uranus. But we have very poor imagery of Miranda, so it's hard to tell if it's the same kind of feature or not. So this is something very unique to Venus. They are generally associated with volcanism. We see little volcanoes inside of them. We see big volcanic flows coming out of them. We see the same kind of radial and circumferential patterns that we see around volcanoes associated with these structures. Studies of these have been used to indicate where parts of Venus may still be active today. So we might actually have not a dead planet, but a very active planet that's still having earthquakes, still having disruption, still having volcanism. So where we're seeing the red dots, those are places where people have identified coroni that would still be active. And so we'd still have this kind of very active volcanic activity, tectonic activity happening on the surface. Whereas where it's white, things are dead. So coroni can be a variety of sizes. They can be down to only 60 kilometers in size, or they can be up to 2,100 kilometers in size. This is Artemis Corona. It is massive. That is about, let's say, from Baltimore to Colorado. So it's this huge feature surrounded by Robin at the edge with big volcanic flows coming out of it, ridge belts associated with it, fracture belts associated with it. And there have been studies that suggest that we might actually be seeing subduction here. So subduction is what's happening in the Pacific Ocean, the Ring of Fire, where we get all of the volcanic and tectonic activity, all those earthquakes associated with the west coast of the US and the east coast of Asia. That is a plate tectonic sort of activity, subduction. So researchers are suggesting this might be a sign that there is a little bit of plate activity happening on this planet, associated especially with this one huge massive corona. But coroni can be in all types of shapes and forms. They all look different. I hope you've noticed every picture I've shown you, they look very different from each other. Sometimes they have a complete annulus of these fractures. Other times the fractures go for less than 50%. There are actually features where there's no circumferential fractures at all. And the only reason we would classify it as a corona is if you look at the topography, you can still see it has a big round topographic high associated with it without the faulting. So that is yet a different type of corona. We're still trying to really figure these things out. The problem is that they're unique to Venus and we can't get to the surface. So we're trying to use this data set that is really exciting and gives us a lot of information, but is not as understandable as the visual data sets that we can use for planetary bodies like the moon or Mars or Mercury. So there are models for how coronae form and why these different shapes would form. They are thought to form when you have plumes of hot material coming from the subsurface and coming up, deforming the surface, and then you have collapse under its own weight. This is very similar to what would happen with a volcano. So then the question is, why in some cases would these plumes form volcanoes, and why in other cases would it form a corona? And those answers could be the surrounding stress regime. It could be the composition of the material that the plume is coming through. This might have been a different type of rock that this plume was under. It might be a difference in how thick the crust was or how thick the lithosphere was. Remember, the crust is part of the lithosphere. There's so many variables and people are just trying to tease this out. And they're trying to tease this out because this could be the answer to us understanding what exactly the processes were on this body that is so similar to Earth and yet so different. So just talking again about these radial features on Venus, these are kind of interesting because we do have structures similar to that. This we can actually say, aha, here on Earth, and we can go up to features. Because on Earth, we have a feature called a dike. A dike forms when very steep faults and fractures are filled with lava. So if you go, you can even go around the United States and find road cuts. And sometimes you'll go along a road cut and the rocks will be really light. And then suddenly you see a really dark line of material cutting through it. That's a dike. It's volcanic material. Sometimes it can cut through sandstones or quartzites. It's just a place where there was a fracture, there was volcanic activity, and the lava said, ooh, look, here's a nice fracture. It's an easy place to flow. And so it flows around it and goes and solidifies. Sometimes you then get erosion in that rock that was filled. So this right here is the Spanish Peaks. That middle section right up here was basically the magma chamber of a volcano. So that was the place where all the magma, all the lava was coming from. And the volcano died and it solidified. And all of the rock that the lava was like intruding into eroded away over time. What we're seeing is the magma chamber. And then we're seeing the radial dikes extending away from it. In that previous image, this is basically a map of all of those dikes that can be seen and identified around that central magma chamber. So we've actually got this analog on Earth where we can, when we look at Venus, we can say, aha, that's what's happening. We have these magma chambers, they're growing, there's fracturing associated with that growth of the magma chamber, and then all that lava inside there is like shooting into this easy place. Because why would you try to like burst through rock when you can just take the easy path? There's already a fracture. By all means, let's just take that fracture and fill it up. Another interesting feature on Venus is something called a pancake dome. I wish, does anyone have a quarter? I should have brought one. I always mean to bring one and I never do. I got a quarter?
There you go.
Okay. Can people online see me?
Anybody with $1? Go ahead.
So this is a quarter. If you're online, you can't see this quarter, take out a quarter. This is the aspect ratio of a pancake dome. So that would be how wide it is. That's its circumference. And that's how high it is in relation to its diameter. There's not like, so when we think of volcanoes, we think of like the big, beautiful peaks. We think of Mount Rainier. We think of K2. We think of Mount Everest, right? I mean, that's not a volcano, but we think of those big, beautiful cone shapes. Not these little flat things, but they're volcanoes. There's flows coming out of them. I'm not going to steal your quarter. They're fractured on the surface. If you look at these really closely, you can see a little pit in the surface of some of these. So these are these volcanic features. Once again, why? Why are some volcanoes on Venus like the shape of volcanoes here on Earth, and then other volcanoes are flat and quarter shaped? It doesn't make any sense. There is a theory, or there has been theories, maybe it's the really thick atmosphere kind of compressing them, but that doesn't explain why other features are able to form a totally conic shape. So people are studying this. Do we have somebody?
Yeah, suppose the lava were very ductile, was very thin. Could that make a pancake shield volcano?
It could have something to do with how the viscosity of the lavas. We do know that on Venus, the viscosity of lava is very, very low because we have flows that go very, very long, very, very long. There have actually been predictions that some of these lava flows on Venus are made of something called komatiite, as opposed to basalt, which is just a very low viscosity material. It would be very uncommon. We would almost never find a komatiite flow here on Earth, but there's predictions that that's what we're seeing there on Venus, just because of the sheer length that the lava is able to travel.
Thank you.
Okay.
What's the temperature of the surface? I mean, the atmosphere is hot.
Yeah,
How hot is the rock?
The rock is probably sitting there at 900.
So,
yeah. I didn't go into this, but you probably all know about the rotation rate of Venus, right?
Don't
No?
assume anything.
Don't assume anything. So Venus is really weird. It does not rotate as fast as Earth. If I am remembering correctly, 2 Venus days. No, wait, 3 Venus days or 2 Venus years? It's 2 to 3. Oh, Wayne is nodding. Okay, so yeah, so basically 2 days, 2 rotations on its own axis is 3 times around the sun. It rotates very slowly, very, very slowly. So that plays with, I mean, that's part of the reason why there's no erosion and there's very little wind activity. We have a totally different physical environment in the movement of the atmosphere because of its very slow rotation.
Question,
Mhm.
is it exactly 2 days? Is 3 years?
I don't think it's exactly, but it's really close. It's close enough that they use the 2 to 3 ratio to describe it. Okay, tesserae. This is the last type of terrain I wanted to show you. This is the very, very old stuff on top of those continental kind of crusts. These are generally very high. They're really bright. We think they're bright because they're really rough. They are really rough because they are really, really deformed. Tesserae are fractured so extremely. If you look at this, like one little section I'm showing you, if you go in there and try and figure out the patterns, the orientations, there's, in this particular image, there's a set doing this, there's a set doing this, there's a set doing this, there's a set doing this. There's at least 12 different sets of deformation happening in this one tiny example of tesserae. Basically, we are seeing millions of years of deformation without any erosion to like wipe out and start again. We have no reset happening here. If this was an Etch-a-Sketch, nobody ever shook it. They just drew. So it's this very complex ridge surface. Some places we can see some of this dark material. Remember, in radar, dark is smooth. So some places there's like little areas that have been filled in with something, probably lava. But there's this very extreme overprinting happening. We know that these are the oldest features because we can see those regional plains doing something called embaying. So here on Earth, when we see embaying, it's like going to the coast and you have water kind of creeping in along the shoreline. And say you have a bluff or, some kind of steep cliff, but you can see the water kind of going into any crack along the cliff. Where the water is kind of going in those areas, it's called embayment, where you have this fluid kind of coming onto the high standing surface and flowing into it. And you can see that that's what's happening here with that dark, smooth regional plains material. It's kind of embaying into this higher standing bright material. It's flowing into it. Using the principles of superposition, which is a very basic geologic term, that means that that dark stuff is younger and it is trying to cover up this older material. Okay, so what does this mean towards the kinematic history? What do we think we're seeing here? So we analyze these tectonic structures to try and determine the geologic history of the body. And there's two basic schools of thought about what's happening. There are people who think, due to their analysis of the surface, and they've looked at these areas, they've looked at these structures, they've come up with dates and tried to place them in a history. And to them, it seems as if particular processes happened at a certain time. So say volcanism. And there was this period of time when there was volcanism along the entire surface of Venus, and then all volcanism stopped. And then all you had was extension. And that's when all of those graben and other extensional structures happened. And then that all stopped. And then compression. And I'm not doing this in the correct order because I don't remember exactly what order they think these happened. But this idea would be one type of thing happened, it stopped. Another type of thing happened, it stopped. Another type of thing happened, it stopped. They call that directional. The other school of thought is that it was non-directional. We had all of these processes happening at any particular time all throughout history. We know that what happens on Earth is non-directional. So the people who think that Venus might be different and might be directional have done extensive studies dating all of these events and these kind of structures that are happening. And they make a strong case for how it seems like all of the graben are of a similar age and all the volcanoes are a similar age. So what is happening in the planetary geology community as they study Venus is basically identifying places where the directional model is not correct, because it doesn't make sense. Just given what we know about Earth and our history, it doesn't make sense that we would have this period of just volcanism and then a period of just extension. It doesn't fit with what we know of geology of rocky bodies.
What would that do? I mean, if you knew one or the other, what would that do?
It affects our interpretation of how this body formed. It can help us understand what exactly made Venus different from Earth. And that in turn helps us understand the other planetary bodies, especially as we start looking at other solar systems, because Venus is probably the closest body in our solar system to the exoplanets that are being observed now in other solar systems. Those hot Earths that people keep finding are going to be very similar to Venus. Venus is probably far more easy to find in the galaxy than more Earths. Now, that doesn't mean that there aren't Earths out there too, they're just harder to find. So when we look at Venus and try to understand what's happening on Venus, this is going to help us understand and make interpretations as astronomers are going out there and looking at the exoplanets and trying to figure out what's happening on their surfaces.
One thing, you said earlier, one of the possible explanations for why it is because there's no erosion.
Right.
Because it's got such a slow rotation, almost a no rotation. And when you look out at the exoplanets, I don't know if you know the answer to that, but are they finding the same thing, that those hot Earths have a slow rotation, or so they have a thicker atmosphere, Or is it just because of the distance and things like that? Because if there was a faster rotation and there was a possible wind, possible erosion, it might be different, right?
So certainly most of the exoplanets, I believe, have very fast rotations, but I do think they have identified some that are really slow. And I just read an article yesterday or the day before about a sand. They've recently identified an exoplanet that seems to have clouds and a whole cloud cycle like here on Earth, but the clouds are silica sand instead of atmosphere and water.
Right.
Today.
I saw that article today.
Yeah, right. It's so bizarre. Exoplanets. I mean, I don't do that. There are people at APL that do exoplanets. If you ever wanted an exoplanet talk, yeah. I could ask around, see if somebody was willing to talk to you about it.
Yes, we have.
Okay. So it's the critical first step in constraining the various existing tectonic models. That basically my next slide answered your question. So once we can establish what the stress history of the planes is, we can figure out whether or not things happened in this directional model or if it was in fact non-directional, which will help us just understand more about the planet itself and what stresses have been affecting it through time. So we can test this by mapping. Detailed mapping and structural analysis of the regions basically is how we would understand the stress orientations and how the stress orientations changed. And this is all really just coming down to us understanding why exactly Venus is different, why we have these two bodies, both of which are within the Goldilocks zone. We are both close enough to Earth that we should be habitable. But for some reason, Venus has this, it had the runaway greenhouse effect. Something happened to it. It came up with this very thick, very hot, crushing atmospheric change that made it unlivable by any form of life we can possibly imagine. And we really want to know why, because as we go forward into the galaxy and start exploring these other planets, this is not a place we would be able to live. So we really want to explore it as kind of a place we don't want to go to. And I said this as conclusions, but I wanted to quickly throw this in. So lots of activity for past volcanic activity on Venus. There are lots of volcanoes. There are huge volcanoes that are like the size of the Hawaiian Islands. But then there are also smaller little domes that kind of scatter all over the surface. We have found tons of lava flows. But recently, people have been identifying places that we think is relatively recent volcanism. For example, some of these atmospheric missions, we've been able to detect sulfuric pockets in the atmosphere that have been suggested to be overactive volcanoes. So when you see these areas in the atmosphere that are suddenly sulfur rich, it's probably because there was a volcano spewing some kind of ash underneath it and spewing sulfur into the atmosphere. But very recently, as in this March of this year, we actually found the identification of a volcanic event that changed in shape during the lifetime of the Magellan mission. So the image on top was taken during the first cycle of Magellan imagery. The image on the bottom was taken in the third cycle, the last cycle of Magellan imagery. And there are changes in how the radar was looking at the surface. So people have been comparing cycle 1 and cycle 3, trying to find change detection for decades. And when you deconvolved the cycle 3 imagery, every time somebody thought that they had found a change, it actually just seemed to be a change in the orientation of the radar until now. What we have here is this feature up here, which didn't change, and this feature here, which did, and it's labeled. So we have the unchanged vent here and the changed vent there. And then this right here seems to be a lava flow. So sometime in the 4 to 5 years that Magellan was taking images, a volcano blew, the vent changed, there's a lava flow. And that basically means that there was an active volcano on Venus no more than 30 years ago, which is very suggestive of the fact that there would still be active volcanoes there today. This is exciting. Up until now, the only places where there have been active volcanism in the solar system are Earth and Io. Io being moon of Jupiter. Io is way more volcanically active than Earth. It's the most volcanically active body in the solar system. But every place else has been pretty much dead. I guess there's Enceladus as well, but those are water plumes, not volcanism as we know it. So this is new, exciting evidence that Venus is not dead. It's actually still active. If it's volcanically active, it is going to be tectonically active as well. There should be earthquakes associated with all this volcanism. There should be new faults and fractures forming all the time. We have 3 upcoming missions to Venus. There's Da Vinci, which will be going to one of those tesseract rings, and they're actually sent a lander down. So we'll actually be able to try and see if the surface is bright like that in the radar images. Just because it's rough, we know it's rough. It's so deformed, it's rough. But is it also compositionally different? And then there's Veritas, which is another US mission. And Veritas is going to be doing global mapping at a higher resolution than Magellan was able to, including much better topographic data. So instead of having this horrible 1 kilometer per pixel, we'll be able to get 50 kilometers per pixel, 50 meters per pixel, and finally be able to like really start evaluating all these faults and fractures and lava flows. And then there's also the Envision mission, which is an ESA mission, European Space Agency mission. And it is also another radar, but they will be looking at the surface in different different radar bands than Veritas. So we're going to have these 3 new missions. We're going to really look at the surface. We're going to really understand this evil twin of Earth. So we have this body that really should be like Earth. It's really not. And this, our goal is to understand why exactly it is. And that's my last slide.
Yeah,
Do
question.
you have any data? But
So my question is, so, you know, what I'm about to say is I know you don't have the same resolution, not being so close, but from ground-based stations, like so the very large radio telescopes, like in Green Bank, the former Arecibo, the one in China, or if you put together your interferometer arrays, they will do, the very large ones will do radar frequencies, 0.8 centimeters to 10 centimeters, they'll do in that range, right? So is there a way to focus them right at Venus? And you may not get the same resolution as, you won't get it as something as close, but will you be able to see through and get some information that you'll be able to work on in between these missions?
I believe that people have done that with those telescopes. I don't know what the results were. It's not something I haven't really looked at that. I do know though, a little bit sideways at that, but the Parker Solar Probe,
Right.
which is basically meant to look at the sun,
Yep.
has actually been able to get data of Venus as it flew by it. And it's a lower resolution, but it's really interesting to see as you go through, you can actually pick out things like Ishtar Terra, that really large continental high unit comes in really clearly in the bands that Parker Solar Probe is able to see the surface of Venus in. So yeah, there's all kinds of other data sets that we have been able to plumb to try and get a little more data about the surface of this planet. But because of its thick atmosphere and its interesting, it's an interesting place in the solar system, what we really need is that a concentrated mission, something that's like going and getting multiple passes. The holy grail of this kind of study would be change detection. So having these 3 new missions going there, like separated in time, the goal is to find something like this vent that has just been discovered where we could see a change in a lava flow or a change in a linear fracture so that we can actually map out activity on the surface. So that's kind of the real goal. That kind of change is not something we'd be able to do an Earth-based telescope to find.
do you have any idea what the rocks are made of?
So the rocks seem to be mostly basalt. So basalt is what the ocean floor is made out of. It's very primitive rock. It's very basic. It's iron and magnesium rich materials. The surface of Mars is mostly basalt. The surface of Mercury is mostly basalt. The surface, the mare on the moon are basalt. That's very common. A lot of the asteroids are basalt. So it's not unusual that Venus seems to be basalt. However, those highland materials and those really bright materials, we think there's a chance that those might be a more felsic rock, a lighter material, like our continental crust is not basalt. It has been reprocessed due to subduction. And so we have those heavy minerals like iron and magnesium have been leached out. We have lighter materials coming to the surface. So one of the things Da Vinci wants to look at is, can we detect a compositional difference in these high standing terrains that would perhaps suggest that those are more like really continental crust, or is it just more basalt that's just higher standing because it's old?
It looks like we have a question online. Arjun, do you want to go?
Yes, I just had a few questions. So, like, what are some predictions for why Venus could have gone that way? And two, like, if there is like no feasible explanation that Venus could have spoiled naturally, like, could there have been life before since Venus is in the Goldilocks zone?
There's actually a mission being planned now called the Venus Life Finder. So recently there were detections of phosphine. I believe it's phosphine in the atmosphere of Venus, and phosphine on Earth is generally formed in the presence of life. So there is some thought there might actually be life in the atmosphere of Venus, where it can be a little more temperate. So it's hellish on the surface, but some layers in the upper parts of the atmosphere would be more around the temperature here on Earth. There would be water, it would be above the sulfuric acid. It'd be a far more friendly to life environment. You would still have to understand why it's like the life would be floating around up there, but weirder things have happened. So yes, there are some interesting, like right now happening searches for life on Venus. As to why it could be different, what happened, there have been a lot of guesses. Most of them are stabs in the dark, just ideas, stories that we throw out there. Maybe the difference was that there was no plate tectonics. Maybe because Earth had this mobile lid and the rocks were always moving around, that kind of gave us an opportunity to bring more materials up from below, and then also take the materials in the atmosphere and we basically bring them back down into the subsurface. So we have a very active relationship between our atmosphere and our interior. Earth is a system. It isn't just the atmosphere and the surface and the interior. Everything is always going in and out. Volcanoes bring things from the depths and they spew them into the atmosphere. And then subduction brings those materials back into the interior. It's very, very active. On Venus, without having that subduction, we're spewing things out from the interior and we're not bringing it back. It's like staying in the atmosphere. It's just being spewed out there. So one hypothesis is that the interior of Venus became really, really, really dry and depleted in these volatile materials, and they were all just being spewed into the atmosphere. They didn't escape the atmosphere because Venus is a big planet. Like Mars, we think that the atmosphere is basically just dissipated because Mars is so tiny, it couldn't keep an atmosphere in orbit around it. But Venus is big, it can bring an atmosphere. So every time a volcano spewed more gas into the atmosphere just got thicker and thicker. And then runaway greenhouse effect just made the surface hotter and hotter. And it just became worse and worse. So that's one hypothesis. There are many, but it's one possibility.
Okay. Yep, thank you.
Joel, go ahead.
Thank you. Thank you. Great talk. While you're speaking, I was remembering back years and years ago to the Russian Venera missions, and I am wondering how much data from those missions, particularly the visual images, which I think was like 30 minutes or 30 seconds, I can't really remember.
Longest one lasted 6 hours.
And but I remember those orange pictures are just so vivid in my memory. How much that has contributed data for your science?
For my science, what I do, nothing. Those images are actually really hard to get. Until recently, Russia has not wanted to share. They have beautiful pictures of very small parts of Venus. They were enough to verify that it is in fact basalt, so that's exciting. And if you look at some of those pictures, you can kind of see how platy the surface is, which is interesting. It kind of gives you a sense of how the surface environment has interacted with the rocks. But none of the places where they landed were particularly structurally deformed. They all tend to be in the flatter areas. That was for safety reasons. When you're planning a lander, you tend to send your lander to the most boring parts of a planet. Little segue here. My grad school advisor was on the Apollo landing site committee. And while I was at school, he would tell us these stories about how by the time they got to Apollo 18, the scientists were lying to the engineers about how safe a place was. Because we kept landing in the mare, which are flat and safe. And they're like, no, we can land in that highland terrain. It'll be totally safe. It'll be good. They just desperately wanted to go someplace different and see something different and see these different kind of rocks. So yeah, you know, for safety reasons, we tend to go to the most boring places of any planet. We're guilty of this on Mars too. Like the Curiosity rover, we sent it to Gale Crater, which is really cool, but it took us 2 years to get to the interesting stuff because we had to land where it was boring and then drive. And so safety, you got to balance that whole, like, you're not going to get any data if you crash and burn on the way down. So
I have a question.
Thank
So
you.
with this very slow rotation again, and Venus being that much closer to the sun, have you been able to detect any effect from the solar wind? Because there's no magnetosphere to even try and help prevent some of that damage. So is there any evidence that because of the amount of time the solar wind is hitting a particular point where if there was a mission that went around the side that was facing away from the sun, relative to that, there was any change because of that?
I have no idea. I'm sure somebody has looked at that. I'm sure that data is out there. I don't know.
Yeah.
I'm sorry.
No, I apologize.
One question I had was, when are these other missions going to be going?
Okay, so Veritas was supposed to launch in 2027, but NASA delayed it. NASA delayed Veritas because Psyche was late and over budget. So Psyche being the mission that just launched a couple of weeks ago to go to an asteroid in the main belt. So it was supposed to be Veritas in 2027, Da Vinci in 2029, and Envision in 2031. Veritas has now been delayed to no sooner than 2031. So Da Vinci will be first in 2029. And then there's a good chance that Veritas and Envision will be there at the same time in 2031. The Veritas team is working very hard to change NASA's mind and try and get a 2029 launch. So there's a lot of campaigning going on right now with members of Congress to try and get this as a line item in the budget so that we have Da Vinci in 27 or 29 and then Veritas in 29 with a slightly different window so they don't get there. If they got there at the same time, Veritas and Da Vinci are different enough that they wouldn't be directly competing, whereas Veritas and Envision are very similar, more similar. They're doing different science, but they're very relatively similar. But yeah, at this point, it's our young member there will be able to be working on those. He'll be a scientist by then.
David?
No,
No,
I missed his name. The person who asked me the question about the life.
Yeah.
All right. Well, are there any other questions online?
Yes, I have a question. It's off topic. I would like to bring you down to earth and ask you if you have read John McPhee's Annals of the Former Earth.
I have not, no.
Are you aware of it?
I don't think so, no.
He traveled across the United States, roughly on Interstate 80. He began with Anita Harris, ended up with David Love, and it's a geologist's dream. It's the geology of America at 40 degrees north.
That's really cool.
From coast to coast, yeah.
Have you heard of the Roadside Geology book series?
Yes.
Yeah, so I've got most of those.
right, David, we're gonna have you give the book of the month next month.
Yeah, I believe this book won the Pulitzer Prize, if I'm not mistaken. In fact,
what was its name again? Annals
of the Former Earth.
Annals of the Former Earth. I will try and find it. Thank you.
Of the Former Earth.
Yeah.
Yeah, very much. It's available on Kindle, and it's I think worth a read for a layman like myself with an interest in geology, and for a professional like you. Thank you very much.
Thank you.
Okay, one other hand. Yeah. All right, that was really terrific. Yeah. Okay, so moving on, we have our regular what's out in the sky this month, and it's not listed, but Phil, you're up.
Okay. Welcome, everyone. So this is just a couple of minutes of solar.
Excuse me, we're seeing the presenter mode.
Okay, yeah, okay. So as we're getting, as Victor's switching the view, it's just going to be a couple of minutes here of what's going on with the solar. Bob, I know you're on, Bob Savoy. This will be the plan for the January Astro School to do a deep dive into some of the solar stuff, because it's more and more and more and more in the news all the time because of the amount of activity. But I wanted to talk about just for a couple of minutes about solar flares, especially since there's a more extreme news with extreme predictions from those who like to talk about the doom and gloom possibilities. But solar flares happen when the magnetic fields of the sun during the solar cycle as it advances, they twist and twist and twist like a rubber band getting twisted. And when when a rubber band breaks, you know what it does, right? It just releases like that. Well, the same thing happens with the magnetic fields, and they release an incredible amount of energy when that happens. And that's what causes these solar flares. Now, what some people don't know too is when these magnetic fields reconnect, they also release a tremendous amount of energy. So these solar flares happen, and there's all kinds of solar flares. You're going to see reports. You don't ever see reports for A, B, and C because they're so weak. They don't really have any kind of impact on Earth. But an M-class will, and it causes the auroras and all these other things. And then you have the X-class, which are the strongest flares. But when it's called X-class, it is the highest level, but that doesn't mean it's the most intense flares that are out there, because there's X1, there's X2, there's X3, there's X4. And what I've got up here is on, I believe it was in 2023, I thought it was in 2003, there was a flare that was so strong that it was figured to be X45. So to give you if you look in the middle box there, an X-class flare produces 10 times the energy output of a C-class flare and 100 times the energy of an output of an M-class flare. But the X-class flares, when you get to 10.3, that's 3 times at X3, 3 times the power of an X1, and X45 is 45 times the amount of energy release as an X3. To give you an example, what I've got there on the bottom is the 10 million times an X-class flare is 10 million times the energy released from a volcanic explosion. So when you take that and if you look at an X-45, what that would mean, how you could picture this is, but even with that type of energy release, it's still just less than 1/10 of the total energy of the sun that's released every single second. So everything like we were talking about just a minute ago is when you're talking about astronomy and its magnitudes. I mean, it's just unbelievable what could be done there. But these flares are just fascinating when you understand what's going on and how they happen. And we're learning more and more about this because of the Parker Solar Probe and some of the other science that's going on around that. If you want to, I made some notes here because I put up a couple things that people may not have heard of. ERGs, for one thing. Basically 10 million ergs, 10 to the 7th, is 1 watt, equal to 1 watt. So when you so it'd be
10 to the 25th watts.
so 1 calorie equals 4.2 times 10 to the 10th, or 42 billion ergs. So when you see these kind of numbers up here where it says the energy released during the flare is typically in the order of 10 to the 27 ergs per second, you could do the math. I mean, and I've got books down here you can see, which it dives real deep into the science, and everybody be poking their eyes out if I start jumping into that tonight. But anyways, I just wanted to point out that there's a lot to these solar flares. What makes them happen? We're in a very intense time where we have real danger of things happening to our communications network, to passengers on airplanes with higher radiation as you get near the poles that they're exposed to, and the astronauts and satellites and stuff are certainly at risk of getting some severe damage. But fortunately, with the Solar Dynamic Observatory and stuff, we know when these happen, and we can start shutting down things in order to minimize the damage, because we have some warning before the ionized plasma gets here. The radiation, you can't do anything about it because that's coming at the speed of light. So anyways, there's your solar minute for this meeting. And then in January for Astro School, there'll be a deep dive into the solar stuff. Yes, Ken.
What does that last sentence mean? Less than 1/10 of the total energy of the sun is released every.
I'm sorry, so it was just a bad grammar on my part. They put in a slide together, but so the 10 million times the energy released from a volcanic explosion is what an X-class flare looks like. And to put that in perspective, that number is less than 1/10 of the total energy of the sun released every second. So 10 million times the energy released from volcanic explosion is equal to less than 1/10 of the total energy of the sun that's released every second. So it's just showing just how gigantic the amount of energy coming from the sun is all the time. So even though that's a massive number that could do an awful lot of damage relative to the total power of the sun, it's like nothing. Any other questions? Okay, I hope you enjoyed this.
Thanks, Phil.
Back to you, Victor.
Yes. I believe that, hello. Jim, are you on? I think he had a conflict and he wasn't going to make it. So I'm going to just go through in the interest of time. There's his slides. Jupiter is really good right now. Saturn is still good, especially if you get out early. And the landed meteor shower is coming this Friday night. I can't do justice to all this good stuff like he can. So, and then there's this Comet Lemon, which I didn't really read up on. So I'm going to just move on.
Yeah, Comet Lemon's a tough one to get. You got to watch for it moving because there's no tail. So it's hard to identify flat out.
Wayne, you want to go?
Okay, so I want to talk today about a new mission from the European Space Agency by the name of Euclid. They just recently, on November 7th, released their first science quality images, as opposed to, it's not first light in the sense they had previously released a few images, but these are their first science quality images. So Euclid is a European Space Agency mission that had contributions from NASA. I think NASA provided some of the infrared detectors. It was launched to the Sun Earth L2 region, just like JWST, back on July 1st of 2023, and it went up on a Falcon 9 from SpaceX. The main mission is to survey 1/3 of the sky to deep limits and spend 6 years doing it. So in the figure down in the lower right, you've got a diagram of the entire sky shown in galactic coordinates. So the galactic equator is horizontal across the center, and the north and south poles are at the top and bottom. And the yellow dots are the places they're going to do deep surveys. So they're going to go really deep and try to get their most distant data. And the regions outlined in blue are where they're going to do their wide survey. So they're basically avoiding the plane of the Milky Way because of all the gas and dust that would be obscuring the objects in the deep universe. And they're also avoiding the plane of the ecliptics. That's that kind of S-curve shape that goes, from the lower left to the upper right. And that's because of the interplanetary dust, and in particular, the zodiacal light that would interfere with the ability to see deep in the universe. So the purpose is to learn about dark matter and dark energy, or provide observations that can give us insights into those two unknown pieces of the universe, or most of the universe. And it will create the largest 3D map of the universe yet made. The telescope is only 1.2 meters in diameter, so it's smaller than Hubble and considerably smaller than JWST, but it has a much wider field of view than either Hubble or JWST. They have two instruments, one called the visible instrument, or VIS, which sees 100 times more area than JWST's NIRCam. This is why they're able to do a survey mission, so that they'll do the survey mission, and the things they find, they will look more carefully and closely with JWST and the Hubble Space Telescope. The second instrument is a near-infrared spectrometer and photometer. So I'm doing this kind of quickly in the interest of time. So if we can go to the next slide.
Are they wide because they just have a huge sensor?
It's probably a combination of both the sensor and the focal length. So I'm going to go quickly through these science images because I encourage you to go look at them yourself, because frankly, showing them on your computer screen over Zoom is not going to do them justice. You can zoom in and see tremendous amounts of detail in them. So the first one is a cluster of galaxies near and dear to my heart, the Perseus cluster of galaxies, which is about 240 million light years from the sun. And this image was taken with both the visible instrument and the near-infrared imager and spectrometer. And you can see the wavelengths of 0.7 microns, 1.1 microns, and 1.7 microns. And this is only about 5 hours of exposure time. And I do want to point out for the imagers out there that H alpha is in the blue channel in this image and in all the others I'm going to show here that they released. And so we see thousands of galaxies in this image. And if you zoom in on it, you can just see galaxies as far as you can go. And since the purpose of the mission is to make observations to inform us about dark matter and dark energy, they're going to use observations of clusters of galaxies to look at background galaxies even behind these clusters, and those distortions in the background galaxies will give us information about where the dark matter is, or where the matter is and dark matter is in these clusters via weak lensing. So that helps us understand the distribution of dark matter. So next. Next slide.
You don't see the...
Yeah, I do now. I do now. So here's the spiral galaxy IC342, which is often called the hidden galaxy because it is only at a galactic latitude of about 10.5 degrees. So there's a lot of dust in the Milky Way. This is as large as the full moon in the sky, or nearly as large as the full moon in the sky. So it's a very large galaxy. If it wasn't hidden by the dust, it would be a spectacular one to image from the ground. Again, same filters, but this is only about 1 hour of exposure time. So this again illustrates how they can do a survey. And so this wide field view of the galaxy will allow these astronomers to study the star formation history throughout the galaxy, this galaxy. Hubble observed the core of this galaxy, but not any of the outer regions. So we've got good, clean detail in the core, but not so much in the outer region. And they're going to observe galaxies like this because mapping galaxies through space shows us the distribution of dark matter, because matter and dark matter, they believe at any rate, are commonly found together. So next slide. This is a globular cluster within the Milky Way. It's about 7,800 light years from the sun. This is again about an hour exposure time given the same filters. And images of globular clusters will be used to look for tidal tails. As the globular clusters interact with galaxies and stars get stripped from the globular cluster in these, what physicists would call a collision, we get streams of stars behind due to the tidal forces between the globular cluster and the galaxy. And if they don't see these tidal tails, that might indicate that there are dark matter halos around the cluster. This would be because if there's dark matter at that concentrates at the scale of globular clusters, the stars in the cluster are actually bound more tightly than we would expect by looking just at the starlight and the mass implied by the starlight. So if we don't see the tidal tails, that means the stars are more tightly bound than we think, and therefore there's probably dark matter at the scale of globular clusters. Again, trying to relate these observations to the mission of the spacecraft. So next. And last, here's the Horsehead Nebula. I find this image interesting because it shouldn't be in their zone of observation. It's near the galactic equator and stuff. So I'm not sure how they observed it. Nonetheless, they did. And again, I want to point out this is a 1 hour exposure, and H alpha is in the blue channel. For those of you who have ever imaged it, you know that all that blue stuff up above the Horsehead is usually really red in our pictures. Well, it's blue here because that's where the H alpha light is. Astronomers hope to find many Jupiter-sized planets and brown dwarfs in this particular set of observations, not just in others. So that's what I wanted to tell you. Here's the website for this press release, which includes all these images and a couple more that I didn't include. And I highly, highly recommend you go look at these images and study them, because they are fantastically pretty images, much wider field of view than either JWST or HST. And I think that's it.
Thanks, Wayne. That's really cool.
You're gonna have to step through the pictures.
So we've only got about 15 minutes and we got a lot of nice pictures. So Jared, are you on? This is I didn't take good notes. There was a lot of photos. I think this is the Lion Nebula, and it's gorgeous. It's just an amazing photo. And here's is this the Cave Nebula? What is that thing?
Yes, this is the Cave Nebula.
Yeah, that is just another beautiful picture. Jared is he's dedicated. He's taking a lot of photos these days, a lot of data. Travis, are you still on?
Oh my gosh, unfortunately, it looks like he left. And yeah, I'm disappointed by that, because he looks like he could really have benefited from this. I wish he would have been here.
I seem to have lost the Zoom meeting. Victor, can you hear me?
Yeah, I think we lost the office too.
I think we lost him.
That's weird, because who's the host?
That would be Victor.
Yeah, but I'm not sure how you find out who the host is as a non-host.
He said he's made Manish Sudar host.
Oh, Arjun, your host, are you still on?
If you go into
Arjun! He's coming on. I hear him.
Arjun, by the way, you're president next year.
Aha!
I think I'm a bit too young for that, and I don't think I'm ready to take on that responsibility yet anyways.
Okay, we can make you like second vice president.
Yeah, sure, that works. Hold on, where's
Awesome.
Can you see my video?
but you are the host.
You
Yeah.
were starting to share, but now I lost it.
Coming up.
No, I was
And
I
now
was
Victor.
running this on a different computer. I'm doing like school homework right now, so I'm like doing this and that, so I wasn't touching anything on here. I don't know.
Yeah,
why.
I mean,
Okay.
you're
Victor's
obviously
coming back.
multitasking.
Yeah, it looks like Victor's coming back. Maybe.
Yep, room is back.
Hey guys, welcome back.
Okay, you should hear us now. You hear us?
Yay!
Yeah, we can hear you now.
Computer went dead, so
Oh,
he's gonna have to bring up the slide and do share screen again. We got about 14 minutes.
Stupid batteries.
Yeah. No, it was it powered in, it was his computer just flipped out. It was,
no, I was going to say they have solutions to batteries.
yeah, it was a solar flare that was earth facing. It was very tightly focused on Robinson Nature Center.
It's actually because I'm in the room. I kill computers.
Oh, is that what it
My
is?
hidden power is there's I put on the aura.
That's what we
destroys
gotta
all
tell the
the-
geologists if you're of any kind.
People think I'm joking until it happens to them.
There we go.
So yeah, we were on Travis's picture,
Yeah. We'll go right
and
back.
it was a shame he wasn't here for this.
Wait, no, are you not here anymore, Travis?
No, he checked out.
Oh, boy.
He had to go help his son.
Because wow,
Yeah, well, wait till you see the next one.
Well,
Yeah, that's a lot of detail in that nebulosity.
I can't believe he's only been imaging for a few months.
ah,
there you go.
Are you guys seeing the full
It's
screen
the
now?
wrong share.
No, we're seeing the presenter mode.
We have to go the other way.
Go up to display settings and swap.
There you
Now
There you
we
go.
see you.
wow.
Yeah, it's really ridiculous. Wait till you see this next one. Look at that thing.
Wow.
That is the flaming star nebula, like I've never seen it. I don't know what he did to make it look like this, but it looks very different from any flaming star image I've seen. It's very, very cool.
Wow.
Wait.
Nebula called?
Sorry?
What's that nebula called? Repeat that one more time.
Flaming star.
That's
Ooh.
the one up by what is it? Alcade? Not Alcade. Alnatoth?
No, it's near,
Oh, I'm thinking of the Flame Nebula. Never
yeah,
mind.
that's
Okay.
not the flame, it's the flaming star.
Okay. Okay.
Yeah. Okay, Jim is not on, but he took some Jupiter opposition and he took some solar eclipse stuff from New Mexico.
Okay.
Are you guys seeing the little animation?
Yeah.
Yes.
Oh, that's awesome.
I would-
Perfect.
I really wish that I would have been somewhere that I could see that. I'm hopefully gonna
Wow.
make it to the next one. Phil, our own sun solar tick.
Yeah, this was on November 5th, Sunday, November 5th. It was fantastic to look at. There was not any large prominences coming off the edge. There's certainly several around there, but the surface detail on the chromosphere is fantastic. And if you had a better view than we have with this projector in here, you get almost a 3D effect when you zoom in on those filaments. Just fantastic, and the amount of activity was on there. I put my Bino viewer on, and it popped in 3D, and it was just incredible to watch. That was done with my 60mm Lunt H-alpha scope with a 2x Barlow in there, and putting the camera on the end of it.
Those filaments look like they might be on Venus.
Yeah, I mean, it's incredible. If you were to stretch that half or 3/4 circle out there, that's going to be over 300,000 miles long.
That's amazing.
And I can't tell how far up it is.
James, are you on by any chance? I think I copied the same picture twice. There's one where he caught a because I was doing it at the last minute right before this meeting. But James, you're not on, are you? Yeah, he actually caught a transit to one of the moons in its shadow. It was really pretty. And then James's other image is, hello. Whoops, it jumped. My computer is losing it. Oh, it's going backwards.
Backwards is forwards.
Thank you for that. It's just my computer's having a hard time today. Might be time for a new one. It's super laggy. There we go.
There we go.
So this is his conjunction Venus and the moon in 2 different exposures. Sounds like a musical thing. Stefan, are you on?
Yeah, Stephen. Yeah, this is Comet Lemon. We were talking about that earlier. Yeah, it's very faint. This is with my 14-inch, and it's moving so fast that I had trouble taking an exposure that wasn't blurred. It's moving. It was moving. Well, that frame is about 1/4 of a degree across, and that's a 20-minute animation. So, and it's getting fainter now. I judged it to be around 12 or 13th magnitude at the time. And in the bottom picture, you can see that I did pick up a little hint of the tail, but it was pretty tough. And we've been fortunate to have some nice clear nights, but I think on that night there were some high thin clouds going across. But this was on the 11th, which was, I think, the day after the closest approach.
Charles Messier would be proud.
Yeah.
You want to say anything about your
Oh, and the other IC 1396, that's 32 seconds with the Hyperstar F2 on the 14-inch.
Single exposure?
No, that's a 10-second mosaic, 10-section mosaic. It's pretty big. The field of view of the camera is about 2 degrees with the Hyperstar, so you can see how big that thing is.
Wow, nice.
Yeah, it's a nice object, but you really have to work to get the whole thing in.
Well, with your big old scope.
Yeah.
Jim, are you still on?
Yep, I'm still on. That's M33. That's M33 and hydrogen alpha
fireworks
added to the red channel and LRGB otherwise.
That is a lot of H-alpha you put in there. That's just beautiful.
Thank you.
I think this is one of my favorite pinwheels. I just did a pinwheel and I don't like mine anymore after seeing yours.
Yeah, it's really nice to see the H-alpha stuff following the spiral arms.
Yeah.
It's the fireworks, right?
No, it's triangulum.
Triangulum, or sometimes called pinwheel. M33.
Beautiful.
Thank you.
It does look like fireworks, though. I can see why you want to say that. I love the way you framed it too. Anyways, thanks for sharing that. And then I've got two, this one is, it's my little, it's not anywhere near Perseus, but it's my little galaxy cluster. It's the Deerlick Galaxy and neighbors, and Stephan's Quintet over in the corner. And this was taken with my 5-inch refractor from a dark site with 90 2-minute exposures. And then I went to HALO, and this is using the 6-inch refractor at HALO under Bortle 5 skies. This is 90 3-minute exposures. And because the camera sensor is bigger, I was able to get Stephan's Quintet, the Deerlick, and then this other little cluster of galaxies over here. But it, if you want a pixel peep, 90 2-minute exposures from Bortle 3, in my opinion, is better than 90 3-minute exposures from Bortle 5, even with the bigger telescope.
I've always thought that.
That's what I always say. Anyways, that's the last of the images. I thank you guys, everybody. Thank you so much for being here. Thank you again to our speaker. It was having you here. And we have only 5 minutes. I'm going to stop the recording, and then maybe if anybody wants to chit chat for a little bit, but then we're going to have to vacate so that the Robinson people can get home.
Have a nice day.
Thanks,
See you,
Dan.
Daniel.
Bye, everybody.
Bye-bye, Wayne.
Thank you, Victor, for making all this accessible.
Excellent pictures, Victor.
Oh, thanks, Dwayne.
Great meeting. Take care, everyone. Have a happy Thanksgiving.
Yeah, thanks. Who said that?
Yeah,
Me.
great meeting, everybody. It was wonderful seeing Debra and Wayne and Phil with their minor shows. Thank you.
Thank you, Bob, and thank you for putting me in contact with Debra. It's a great speaker, and I was right at the beginning when I said that we had a good speaker.
It reminded me of the space station cutting through.
Yeah.
Does anybody do any work with gravity, or when you wind everything up? Is there a memory involved with that? You wind up all that stuff and you you release it.
It's not the gravity. It's just the from that's when those magnetic fields break after wrapping like they do. So when it's tied to the solar cycle. So every 11 years approximately, the poles flip, and then the magnetic fields are basically parallel.